In this video, we're going to look at a couple of examples of the conic section parabola. One example in which we'll graph a parabola given an equation, and one example in which we'll go the opposite direction, come up with the equation based on information about the graph. While we graphed parabolas back in Chapter 2, in this unit we're adding a couple of aspects of the geometric definition of a parabola, namely the focus and the directrix. The fixed point and the fixed line from which every point on a parabola is the same distance. Also recall that we're adding in the possibility of a horizontal parabola. Notice the difference between the two standard form equations. The vertical parabola, one that we're used to seeing, has the x as the squared term, and in the horizontal parabola the y term is squared. For either one of those equations, the ordered pair hk is the vertex of the parabola, and for both, a equals 1 over 4p, where p is the distance from that vertex to the directrix. Remember that the focus is going to be inside of the parabola, regardless of whether it's vertical or horizontal, and the directrix is going to be perpendicular to the direction of the parabola. Let's look at a particular example. For this, what I would like to do is graph the parabola, marking all of its most relevant points. The vertex, obviously, x and y intercepts, if applicable, but also the focus and directrix. Before we get into the algebra and putting it into standard form, let's notice a couple of things. First of all, there is no x squared term. There's only a y squared term. Because there's only one quadratic term, that indicates that this conic section will be a parabola. And because it is the y that is the quadratic term and not the x, we can safely assume that this is going to be a horizontal parabola. Like when we graphed circles on the previous video, our goal is to take the equation on the left and turn it into a standard form equation on the right. Remember, that requires that we make a binomial squared. That means we need to create a trinomial square in the equation. In this case, we are going to group the y squared terms together and leave a space for a value that could create that trinomial square. The other values, we're going to go ahead and move to the other side of the equation by subtracting from both sides, but we're also going to leave room to add that same value to both sides. Remember, when we're completing the square, we're going to take 1/2 of the middle term, that's 3, and 3 squared is 9. And when we do add that to the left-hand side of the equation, we also need to add it to the right-hand side of the equation. When we factor the trinomial square, it becomes y plus 3 squared, and that is equal to negative 8x minus 16. Now this a term, technically speaking, it could reside on either side of the equation. For ease, I'm going to move it in front of the quadratic terms, so we need to find out what that value is going to be by factoring out a negative 8 on the right-hand side, leaving x plus 2 inside the parentheses. To move that negative 8 to the left-hand side, I'm going to divide both sides by negative 8, and so what I get is 1 divided by negative 8 times the quantity y plus 3 squared equal to x plus 2. Now that we have this equation in standard form for a parabola, we'll be able to graph it by using the different parts that we know. We know that the vertex is going to be negative 2, negative 3, so we can go ahead and plot that point. And now let's plug in some other relevant values to help us find other points that might be helpful. The first one that might be easiest is to actually find the x-intercepts by plugging in 0 for y. 0 plus 3 squared still inside the parentheses. So we have 0 plus 3 squared, that's going to be 9. So we have negative 9/8 is equal to x plus 2. And when I subtract 2 from both sides, we're going to have to use a common denominator. So that's minus 16/8 is equal to x. So the x-intercept is negative 25/8, or just a little bit more than 3. So I've plotted that x-intercept there. That's the point negative 25/8, 0. Remember, though, that parabolas are symmetrical, that there's an imaginary axis of symmetry that runs right through the vertex, an axis of symmetry, and that this point, negative 25/8, has a corresponding point exactly on the opposite side of that axis of symmetry. So if the vertex is at a y value of negative 3, this symmetric point will be down here at negative 25/8, same x value, but at negative 6. These 3 points give us enough information to graph our parabola. Now normally I would go back and try to find my y-intercepts as well by plugging in 0 for x, but notice the points that I've plotted so far indicate that I'm not going to have any y-intercepts. You could double check that if you wanted to by plugging in 0 for x and solving for y, and you would get a complex number. The last thing that we need to do is plot the focus and the directrix. This is what's new for us in terms of parabolas. Remember that the a value, that leading coefficient, in this case negative 1/8, is equal to 1 divided by 4p, where p is the distance from the vertex to the focus and the directrix. So in this case, negative 1/8 is equal to 4p, so that means 4p is equal to negative 8, p is equal to negative 2. Now the negative number doesn't mean all that much in this particular case because it's a distance from the vertex and it's actually going both directions. So the distance that the focus is from the vertex is 2 units. So I'm going to move from the vertex 2 units to the left. That is the focus. It's at an x value of negative 4 and a y value of negative 3. The directrix is going to be 2 units to the right of the vertex in this case. So 2 units to the right is actually the y-axis. And remember that the directrix is an imaginary line. And that line is at x equals 0. So now we've plotted our parabola with our vertex at negative 2, negative 3, our focus at negative 4, negative 3, our directrix at a line at x equals 0, and then our x-intercept and its corresponding symmetric point. Now we're going to go the opposite direction. We're going to use information about the graph of a parabola to write a standard form equation of it. We did this back in chapter 2. Usually we knew information like the vertex or the x-intercepts, or we heard about a maximum point. Now we have more information with which we can write an equation. The focus and the directrix in this case can lead us right to a particular equation. So let's go ahead and plot these two aspects of the graph so that we can start getting an idea of what the parabola should look like. Here's the directrix at x equals negative 2, and then we have the focus right there at 2, 2. Now remember, the vertex has to be the exact same distance from both of these parts, and it falls directly in between them. So if we were to draw a line between the focus and the directrix, you'll notice that the vertex must fall halfway between the two. In this case, at the point 0, positive 2. That's our vertex. Now, that's all the information that we know about this guy right now. I'm going to go ahead and draw a parabola that fits this description right now, but we can use this information to go to our standard form equation. Because this is a horizontal parabola, we're going to use our standard form that includes the y as the quadratic term and the x as only a linear term. Let's plug in the information that we know. We know that the x-coordinate of the vertex, h, is going to be 0, and we know that the y-coordinate of the vertex, k, is going to be 2. So all that's left is the a value. Recall that a is equal to 1 divided by 4p, where p is the distance from the vertex to the focus and directrix. In this case, we found that value to be 2. So 1 divided by 4 times 2 is equal to 1/8, similar to the last problem, except this time that a value is going to be positive. Our parabola is opening to the right, that's the positive direction when working with a horizontal parabola, and so we get the standard form equation, 1/8 times the quantity, y minus 2 squared, is equal to x. Knowing this equation would now allow us to be able to identify any of the other pertinent points. In this case, you already know the y-intercept is actually the vertex, but you could also find the 1x-intercept by plugging in 0 for y.